Such a potent image that the Roman emperors took the title Pontifex Maximus, an honor which eventually passed to the head of the Roman Catholic Church, the Pope, or Pontiff. By 200 AD, there were 7 permanent bridges across the mighty Tiber River. Wherever they could, the Romans constructed their bridges out of stone. Though stone is more difficult to work with than wood, it's stronger, needs far less maintenance, and is an excellent material for building arches. Now, what's special about an arch? Well, just look at the alternative. The simplest way to span a river or valley is with a simple post and beam arrangement. Vertical wooden posts set fairly close together to support a horizontal roadway. By building stone arches like the ones behind me, the Romans were able to span the same and even greater distances while minimizing the number of obstacles to the river's flow and to ship traffic. But what keeps an arch from falling down? The answer is its shape and the weight of the bridge above it. Here, let me show you. Wedge-shaped stones are laid side by side in a semicircle. They are initially kept in place by a wooden form until they are locked together at the top with a keystone. By itself, a stone arch can support very little. And if you add weight to the top, the sides will start pushing outward and crumble. So the Romans placed stones around the arch to counteract this outward thrust. Now, the weight at the top serves to press the individual arch stones together, making the entire arch rigid and capable of supporting very heavy loads. This pressing action is called compression, a force stone bridges handle very well. It's hard to minimize the role of bridges in making Rome commercially as well as militarily powerful. In fact, many of its bridges are still in use today, carrying people and commerce in a modern world that was first linked together by a chain of Roman bridges. But there are some disadvantages to stone as a building material, and for centuries, bridge builders looked for practical alternatives.
Stone bridges worked very well for a long time, but stone is heavy. It takes a long time to build with. So when iron and iron production became cheaper and cheaper, engineers were particularly interested in trying the new material to see if they could build bridges that were lighter, stronger, had longer spans, and were therefore cheaper.
The breakthrough would occur in 1779 in Coalbrookdale, England, where the world's first iron bridge was built across the Severn.
Iron was really the most exciting material of the Industrial Revolution. In fact, iron was the reason it happened, because you couldn't make machinery without it. And then along came the people who tried to build carriages out of it that would roll on iron rails. And these iron horses would, of course, replace the horse. And they would be much faster, and they were. But the problem was they were a lot heavier, too. And once you have these heavier things rattling down the iron rails, you're really creating a lot of problems for bridge builders.
So the great gift of iron was immediately tested by the most difficult challenge bridge builders had ever faced. And the new material failed.
During the early years of the iron railway bridges, there were some catastrophic failures. And railway companies don't like that because it's not good publicity and people were losing their lives. The bridge that really brought the problems of cast iron, I think, to a great deal of public notice was the Dee Bridge failure in May 1847, a small bridge over the River Dee on the Chester and Holyhead Railroad.
The Dee Bridge was designed by famed British engineer Robert Stephenson, who had built several successful railroad bridges, including this elegant stone arch span over the Tweed River. His father, George, rose from being an uneducated mine worker in Newcastle to become the man behind the world's first steam railway in 1825. Father and son worked closely together, designing everything from locomotives to railway bridges. The Dee was a post and beam bridge, with stone piers for the posts and cast iron girders for the beams. Stephenson believed his long cast iron girders could support the weight of a train without too many river-blocking posts underneath. But the weight of a train will sag any unsupported span, and this produces a stretching or pulling force called tension on the bottom portion of the beam. Cast iron, like all metals, contains minute surface cracks and flaws. And if these are stretched, they can grow and could even split apart, which is exactly what happened to the D. The D collapse was studied by England's best engineers. At the inquest, it was not Stephenson's design, but the inability of cast iron to resist tension that was clearly to blame. Fortunately, Stephenson and his colleagues would discover that less brittle metals, like wrought iron and steel, could withstand tension forces very well. And by the end of the 19th century, engineers were using the new materials to take bridge building to unprecedented heights. One of the era's best engineers was Gustav Eiffel. In 1884, he was asked to bridge the windy Garabit Valley in France's Massif Central, a mountainous barrier that blocked the railways from reaching southern France. Eiffel's spectacular bridge changed all that. His huge wrought iron arch supports a single railroad track. And though he used a minimal amount of material for what was then one of the tallest bridges in the world, he counteracted the gusty mountain winds with his design. His open frame arch lets the wind blow right through the bridge. And his supporting towers are built wider at the bottom than at the top, and for good reason. If I stand straight up like this, any force which pushes against the top of my body can easily tip me over. My natural instincts, thank goodness they're still working, are to spread my feet. This stabilizes my legs and centers my weight. This is exactly what Eiffel did with his towers here in Garabit, and 5 years later with his much higher tower in Paris. Garabit was not only an artistic triumph, it was cost-effective too, for Eiffel used a truss configuration to eliminate unnecessary building material without sacrificing safety. When a train crosses a truss bridge, the heavy bottom members are always in tension and the top members always in compression. And depending on the position of the train on the bridge, the connecting vertical and diagonal members will change from tension to compression. But at any given point, these opposing forces stay balanced. A pull on one member is resisted by an opposite push from another, all along its length. So the bridge remains rigid and strong despite its lightness. As the 19th century drew to a close, engineers began spanning distances once deemed unbridgeable. But over in Scotland, the public was still reeling from the collapse of Thomas Boucher's Tay Bridge. So when engineers proposed bridging the even wider Firth of Forth, the public demanded a bridge that would never fall down. And they got it.
Just south of the Tay is the Firth of Forth, and again the railway company wanted to carry their railroad over this enormous estuary. But of course it had just been preceded by a horrendous, massive structural failure. So they came up with this great cantilevered idea.
Critics joke that the Firth of Forth railway bridge resembled a giant dinosaur skeleton, but no one could doubt it was strong. This intricate array of struts and angles is the Firth of Forth railway bridge. It was the brainchild of Sir John Fowler and Benjamin Baker. Completed in 1890, it was the first bridge built primarily of steel. The Forth Bridge is a cantilever bridge. And although it looks quite complicated, the principle is really fairly straightforward. People came from miles around to hear Baker explain it, using his assistants as human cantilevers. The men in the chairs represent the towers from base to top. The diagonal sticks are the thick steel tubes projecting from the base. Their arms are the steel limbs hanging from the top. With the bottom members in compression and top members in tension, the cantilevers support the connecting roadway that the third man sits on. Each main section is also firmly secured at the ends to provide additional support for the central span. And this truss-like configuration helps make this bridge one of the strongest ever built. The highest winds barely shake it, which is exactly what the Scottish public demanded after the Tay disaster. Yet very few like it were ever built again. The problem, it turns out, is not how to design a safe bridge, but how to get a big one built without breaking the bank. It takes so much material to build a large cantilever of this size, most places can't afford them. Fortunately, engineers had developed a more practical solution for long spans, and just in time. New York is typical of many big cities bounded by water. As its population expanded, people settled across the rivers on either side. As early as the 1860s, its neighbor along the East River, Brooklyn, had grown into the third largest city in America. Both metropolises were bursting with immigrant populations. And the East River that separated them was clogged with ferry boats full of commuters and commercial vessels laden with cargo. Everyone was clamoring for a new bridge, but it would have to be strong enough for people and trolleys, high enough for tall-masted ships, and it had to be constructed without blocking all this river traffic. What New York needed was a suspended bridge. This is the Clifton Gorge Suspension Bridge in Bristol, England, designed by the legendary engineer Isambard Kingdom Brunel in 1830. It is a very early suspension design, but as you can see, it still does its job very well. Unlike conventional arch or post and beam bridges, the roadway here is supported from above rather than underneath. It hangs from strong iron rods that are attached to a graceful curving cable made up of heavy iron bars bolted together. The ends of these sweeping cables are attached to huge concrete housings called anchorages, buried deep in the cliffs beyond each of the bridge's towers. Even today, this is a spectacular structure, and as you can see, there's literally nothing underneath to support it. This is how that works. The cables stretch across the two towers and attach firmly at both anchorages. The roadway is connected to the cables by strong metal suspenders. In a suspension bridge, the long roadway is constantly pulling down on the cables. But the housings that secure the cables at either end act as a counter-pulling force in the opposite direction. Like a tug of war, these opposing forces stretch the cables into great tension. And the cable pushes down on the stone towers, compressing them into very rigid structures. In essence, the design transforms the tension in the cables into compression in the towers, creating an equilibrium of forces that allows the bridge to handily support the long central span. The idea seemed perfect for linking Brooklyn and Manhattan across the busy East River. So they gambled that a brilliant German immigrant named John Roebling could build the longest suspension bridge ever, the Brooklyn Bridge. Roebling jump-started his career by learning how to make steel wire into thicker suspension cables. He built 3 suspension bridges prior to Brooklyn, including the beautiful Cincinnati-Covington Bridge over the Ohio River. But his Brooklyn Bridge would need to be longer and heavier than any suspension bridge ever built. And its towers would have to rest in very deep water, something Roebling had never attempted before. In typical fashion, he worked furiously, day and night, on his surveys and calculations, driving himself with a passion that bordered on madness.
John Roebling was an iron-willed, tenacious, courageous, tough, ambitious man who had no sense of humor. He was a mean, terrible father to some of his children, almost beat one son to death. But he was a genius. He was a lesser Leonardo. He wasn't just a bridge builder. He was a mathematician, he was a philosopher, he was a linguist. But his obsession also dealt with time. He could not waste time.
As Roebling rushed to complete his plans, he was working late, standing at the edge of the Fulton Street ferry dock, checking his measurements. As always, he was completely absorbed in his work and stubbornly refused to move as a ferry pulled in, traveling faster than it should. The ferry banged hard into the pier and mangled Roebling's foot so badly it needed amputation.
Roebling wished the amputation to be performed without anesthesia because he didn't believe in anything dulling the brain. He also was a believer in hydrotherapy, or in the wonders of water as a cure. And so he insisted that cold water be poured on his foot night and day, day and night, and that water would cure everything.
It was a terrible mistake, and he quickly developed lockjaw, the always fatal symptom of tetanus.
And despite his hideous, unbelievable pain, John Roebling looked up at his son Washington and said to him, "You will build that bridge."
En dus heeft de rechtbank hier gezegd, wij kunnen deze man niet langer als een verdachte beschouwen. En daarmee is dus ook het laatste spoortje in dit hele dossier is in niets opgegaan. En dat betekent dat het dossier zo goed als dood is.
Ja, en wanneer hebben we eigenlijk voor het laatst iets gehoord van die bende van Nijvel? Want dat was dus inderdaad wel een tijd geleden.
Ja, dat is, ze hebben aanvallen gedaan in de periode september 82 en 85. Een aanslag in Aalst op een supermarkt, de Delhaize, zeg maar de Albert Heijn in Aalst. En daar vielen op dat moment 8 doden, in totaal 28 doden. Het waren aanvallen waar Golf GTI's werden gebruikt, de supermarkt, de parkeerplaats werd opgereden. 4, 5 mensen stapten eruit, werd in het wilde weg geschoten. En vervolgens vertrokken ze weer, bloed achterlatend. Maar weinig sporen, in ieder geval onvoldoende om dit dossier tot een einde te brengen.
Het is ook ineens weer opgehouden, kennelijk. Gert-Jan Dennekamp in Charleroi. Vandaag worden trouwens nog de nabestaanden van de slachtoffers erover geïnformeerd dat het onderzoek is stopgezet. En daar horen we later vandaag nog meer van.
And into a swirling motion, which created many high and low pressure systems called vortices. These in turn forced the bridge to increase the motion it already started.
But it's like somebody on a swing. A little push now, a little push later, exactly the right time, builds up into tremendous amounts. It is called properly a self-excited vibration. The bridge took the wind over and made it cause the bridge to fail.
Even with its design flaws, a heavier bridge might have resisted the wind pressure. But Tacoma was built light to save money and suffered the consequences. Other Moisieff-influenced bridges, even those with stiffening trusses like the Golden Gate, were immediately reinforced with bracing systems that restrain twisting motions in the wind. Movement has not been entirely eliminated. as this 1982 footage of the Golden Gate clearly demonstrates. In high, steady winds, the bridge can move radically up and down, placing tall trucks in danger of blowing over. But in engineering, most things are trade-offs. The flexibility inherent in all suspension bridges may have been the Golden Gate's salvation when, in 1989, a devastating earthquake struck San Francisco once again. People were killed when older and more rigid elevated freeways collapsed. And a section on the eastern half of the two-part Oakland Bay Bridge fell onto the deck below. The other half of the bridge, a suspension structure, was flexible enough to avoid serious damage. But hundreds of California's bridges, including this one and the Golden Gate, needed significant earthquake-related modifications.
When the bridges were first built in the 30s, 40s, and even 50s, there was very little that was understood about earthquake, not just by engineers, but by everybody.
Engineering can be as much a process of learning through experience as it is an exact science. And the knowledge gained from the performance of older bridges make new ones safer, hopefully without a disaster as a lesson. Oakland is replacing its old cantilever bridge with a new earthquake-resistant suspension bridge. The city initially considered a cable-stayed design, similar to the Sunshine Skyway Bridge in Tampa. This economical variation on the classic suspension model has striking diagonal cables that anchor right to the bridge deck itself. Though more and more cable-stayed bridges are being built throughout the world, their design limits their length. For the most daunting spans, the classic suspension bridge is still the best solution. Today, the longest suspension bridge is Japan's Akashi Kaikyo, with a central span that stretches 1.25 miles. Akashi is indeed a wonder of the modern world, the legacy of the Golden Gate and so many other great bridges that came before it.
How are you? Isn't this terrific? Thanks for coming by. Don't forget us. Fabulous. The big money today. Thanks. Don't forget us.
To the dreamers, there are few barriers bridges cannot cross. For them, the next great bridge might join Italy and Sicily, or even cross the Bering Straits to link the United States with Russia. These achievements would continue a legacy that all bridges share. Whether they were built for war or commerce, for foot traffic, trains or cars, bridges have served to connect the people of the world for the continued advancement of all civilization.